Tomorrow, for the first time in over half a century, 4 astronauts will travel to the far side of the lunar surface, farther from Earth than any human has ever travelled. From Earth, it will look like progress, like celebration, like history repeating itself. But the moon does not repeat history gently, because beneath the headlines and the applause there is a quieter truth. Nothing about the moon is passive. It is the most hostile environment our species has ever chosen to enter. Its dust shreds spacesuits and shreds lungs. Its radiation can kill you in under an hour. Its surface temperature swings 300 degrees between noon and midnight. Its quakes last not seconds but hours, and the strangest part, we're going back hoping it remembers us kindly. Stay with me, because what comes next will change how you see every small step ever taken beyond Earth, and why the next one might not be as simple as it looks. Before we begin, if you genuinely enjoy what I do here, feel free to subscribe and turn your notifications on, because we're going to follow this mission from beginning to end. From the countdown to the moment they slip behind the far side of the moon and everything in between. Now, settle in and let's ease into it. 2. Part 1. The celebration moment. Tomorrow, 4 human beings will do something no one has done in over 50 years. They will leave Earth orbit, fire their engines toward the moon, and loop around the far side of a world that most of us have only ever seen as a soft silver glow above the tree line. 4 astronauts strapped into NASA's Orion capsule, arcing outward into a trajectory so extreme that at its farthest point, they will be farther from Earth than any human being in the entire history of our species. Let that land for a moment. Every person who has ever lived, every explorer, every sailor, every astronaut, none of them have been that far, and the world is going to celebrate. The news will show the launch. Social media will light up. Someone's going to cry watching it on their laptop at 2 in the morning. And honestly, they should. It is genuinely extraordinary. It is our Timus II, and it represents something real. The moment humanity declared itself a lunar species again. The emotional weight of this is not manufactured. Apollo was the last time we did this. And Apollo ended in 1972. That is more than half a century of absence. An entire generation, actually 2 entire generations, grew up on a planet where human beings simply did not go to the moon. The moon became something you admired from a distance, something that belonged to history, to old photographs with grain and dust and men in bubble helmets. And now, suddenly, we're going back. The nostalgia alone is overwhelming. You can feel it in the press conferences, in the way the astronauts speak about standing on the shoulders of the Apollo crews, in the care NASA takes to frame every announcement as a continuation of something sacred, rather than just another government mission. And there is something to that framing. There genuinely is. But here is what the celebration is not saying. Here is what the coverage is quietly stepping around. The thing that the triumphant music and the slow-motion launch footage and the interviews about human courage and scientific progress are carefully not mentioning. The moon is not waiting for us. It is not a prize sitting on a shelf, patient and inert, ready to be claimed by whoever shows up with the right hardware. It is not the grey, quiet, geological museum we have been picturing since grade school. The moon is something far more uncomfortable than that. And the farther those 4 astronauts travel from Earth, the closer they get to an environment that is at every level in every direction through every mechanism available to physics and chemistry and biology built to unmake them. That is not a metaphor. That is a description of what the science actually says. And by the end of this, you're going to understand exactly why the engineers who know this mission best sleep a little less soundly than the people watching the launch from their living rooms. Part 2, the missing context. Here is something worth pausing on because it matters more than the press releases suggest. Our Timus II is not a landing. The crew will not touch the lunar surface. They will not plant a flag, collect a sample, or take a single step in 6th gravity. This is an orbital flyby, a crude loop around the moon designed to test the Orion capsule and life support systems in deep space conditions before the actual landing missions follow, which sounds, when you say it that way, almost like a technicality, almost like they are getting close but not quite there. And so, the real risks are still somewhere in the future, except that is not how the physics works. The trajectory of Artemis II crosses the full lunar hazard environment. The radiation field does not care whether you land or not. The solar particle exposure does not check your mission profile before deciding whether to intensify. The deep space environment that exists around the moon, the one without Earth's magnetic field wrapping around it like a protective cocoon, the one with no atmosphere softening anything, that environment begins well before you reach the surface. Apollo missions were measured in hours of surface exposure. Some of them were barely days in total duration. Artemis 2 is designed to push beyond that to test endurance in deep space, at distances and durations the Apollo program never approached. So when the engineers run their risk models, they are not modelling a brief visit. They are modelling a transit through a hazard zone that does not end when the capsule loops back toward Earth. The public perception and the engineering reality are quietly, politely not the same thing, and that gap matters because what comes after Artemis 2 is not another flyby. What comes after is people on the surface staying longer, going back repeatedly, eventually if the plans hold, building something permanent. And to understand whether any of that is survivable, you first need to understand what the moon actually is. Part 3, the core claim reveal. The moon is not passive geology. That is the sentence I want you to hold on to because everything that follows in this video is an explanation of what that actually means. We have a cultural image of the moon that is essentially a very large, very old rock, inert, stable, conquered once, therefore conquerable again. The Apollo astronauts walked on it and came home, and we took that as proof that humans can handle it. And in the narrowest technical sense that is true. They did walk on it and they did come home. But here is what Apollo actually demonstrated. It demonstrated that with the right equipment, under the right conditions, with a mission profile measured in days, human beings can survive a brief visit to the moon. What Apollo did not demonstrate, what no mission has ever demonstrated, is that the moon is compatible with long-term human presence because it has never been tested. And the science that has accumulated since the last Apollo crew left in 1972 paints a picture that is, to be honest, significantly more alarming than the history books suggest. The moon has no atmosphere. You probably know this, but the implications of having no atmosphere go far beyond the obvious inconvenience of not being able to breathe outside. No atmosphere means no buffer between the surface and space. Every particle that travels through the solar system, every charged ion, every ultraviolet photon, every high-energy cosmic ray fired from a dying star somewhere across the galaxy hits the lunar surface at full, unimpeded velocity. There is nothing to slow it down, scatter it, or absorb it before it arrives. On Earth, our atmosphere is effectively a shield we never notice because we have never lived without it. On the moon, that shield is simply absent. You're standing unprotected in open space on a rock, and because the moon has no atmosphere, it also has no erosion cycle. No wind, no rain, no rivers grinding boulders into sand over millions of years. The surface of the moon has been shaped almost entirely by impact events, meteorites and micrometeorites, striking at extraordinary velocities over 4 billion years, and nothing has smoothed the results. The particles that make up the lunar surface are not like sand. They are not rounded and worn. They're jagged, angular, fractured at a microscopic level into shapes that, under any electron microscope, look less like soil and more like shattered glass. And those particles are chemically reactive in ways that Earth's soil simply is not. Because on Earth, chemistry reacts with water and air and living organisms and changes over time. On the moon, the particles are frozen in a state of chemical readiness that has barely evolved since they were formed. So what you have when you combine all of this is a surface environment that is not simply the absence of comfort. It is the presence of active compounding hostility. The dust is a biological hazard. The radiation is a permanent background threat that escalates without warning into an acute emergency. The temperature range exceeds what most materials on Earth experience in an entire lifetime, cycling through it twice every lunar day. The ground beneath your feet is seismically active in ways that are only now being fully understood. And none of these hazards exist independently. They interact with each other, reinforce each other, and stack into a single survival problem that humanity has never been forced to solve for longer than a few days at a time. Apollo is proof that we can visit. Artemis is something else entirely. Artemis is the moment we find out whether we can stay. Part 4, the first shock list. Let me give you a preview of what staying actually means, because I think the specific details are more alarming than the general warning. The dust on the moon is not like any dust you've ever encountered. It is not the soft grey powder it looks like in photographs. At a microscopic level, lunar dust particles are shaped by billions of years of violent impact events, with no erosion to soften them, which means they have edges, real, cutting edges, at a scale so small they can bypass the natural filtration mechanisms in human lungs. We have laboratory data showing that simulated lunar dust causes oxidative stress in lung cells, DNA damage markers, and inflammatory responses in tissue cultures, and the laboratory simulants we use are almost certainly less reactive than the real thing, because the actual lunar surface particles are space-weathered in ways that ground-based simulations cannot fully replicate. The radiation environment on the Moon, measured directly by instruments on the lunar surface, runs at approximately 1,369 microsievert per day. To put that in perspective, the average person on Earth receives about 3 microsieverts per day from background radiation. That means standing on the Moon on an ordinary quiet day with no unusual solar activity, you're absorbing roughly 200 times the radiation you would receive on Earth, and that is the baseline. When the Sun decides to produce a solar particle event, which happens without reliable warning and can escalate from nothing to potentially lethal dosage within an hour, the numbers stop being academic and start being immediately life-threatening. The temperature swings reach from positive 127 degrees C at lunar noon to minus 73 degrees in the lunar night. That is a 300 degrees range cycling repeatedly, stressing every material, every seal, every mechanical joint in every piece of equipment anyone brings to the surface. In the polar regions, where the ice deposits that make long-term habitation theoretically possible are located, temperatures drop even further, approaching minus 250 degrees C in permanently shadowed craters. Those are temperatures colder than Pluto, and underneath all of this, the ground itself moves. Apollo seismometers recorded over 13,000 seismic events during their operational period. The Moon is not the dead world we assumed. It has quakes, not the familiar rolling kind that Earth produces, but something more unsettling. A ringing quality caused by the Moon's rigid dry crust that allows seismic waves to reverberate for minutes, sometimes hours rather than the seconds an Earth-bound tremor lasts. Every single one of those hazards exists simultaneously. They are not a list of separate problems to solve one at a time. They're a single compounded environment that a human being must survive in all at once continuously for weeks or months. And the terrifying truth, the one that the celebration tends to skip over, is that we've never tested whether a human body can actually do that. Not even close. But before we get to what we do not know about the human body on the Moon, let us start with what we do know about the dust. Because the more you learn about it, the more you understand why some of the engineers who study it call it the most dangerous thing up there. Part 5. Not soil. A world made of shattered glass. Imagine taking a piece of glass and smashing it on a concrete floor. Now imagine doing that 4.5 billion times in a place with no air, no water, and no process of any kind that would round off the resulting fragments. What you end up with is a powder that looks harmless from a distance. Grey, fine, almost softer looking in photographs, but is at the microscopic level a collection of tiny, jagged, chemically active blades. That is what the lunar surface is made of. Not soil, not sand, a world of shattered glass. The scientific term for it is regolith, which is a fairly neutral word for something that is genuinely not neutral at all. Lunar regolith is formed almost entirely by a process called impact gardening. The continuous bombardment of the surface by meteorites, micrometeorites, and cosmic particles over geological time in the complete absence of any weathering process to break down what the impacts produce. On Earth, rock gets turned into soil through a combination of physical and chemical weathering. Water seeps into cracks and freezes and expands and breaks things apart. Acids dissolve minerals. Living organisms digest and transform the material. Rivers transport and tumble it until the edges wear off. On the Moon, none of that happens. The surface gets hit and whatever the impact produces stays exactly as sharp and reactive as the moment of its formation. The mineral composition of lunar regolith is dominated by silicate, the same family of minerals responsible for silicosis in coal miners and sand blasters on Earth, a disease caused by chronic inhalation of fine silicate particles that the lungs cannot expel. The lunar version contains silicate fragments at sizes small enough to penetrate deep into the respiratory system, past the natural filtering systems of the nose and upper airway down into the alveolar region of the lungs, where gas exchange happens, and where the immune system is least equipped to deal with persistent foreign material. But it gets more complicated than that because the surface exposure of lunar regolith gives it an additional chemical property that Earth-based silicate dust does not have. The Moon's surface is continuously bombarded by solar radiation and cosmic particles, and that bombardment creates a phenomenon called space weathering, which alters the outermost atomic layers of each particle in ways that make them chemically reactive in a very specific sense. They are hungry for electrons in a manner of speaking, and when they encounter biological tissue, that hunger translates into oxidative damage at the cellular level. And then there is the electrostatic problem. Lunar dust particles are electrically charged by solar ultraviolet radiation, which means they do not just sit passively on surfaces. They actively cling to everything they touch. Spacesuits, gloves, helmet visors. The surface of a glove that has touched the lunar ground does not just have dust on it. It has dust bonded to it by electrostatic attraction. And that dust, when brought inside a habitat, does not stay where it lands. It resuspends, it migrates, it gets into everything. The Apollo suit showed visible abrasion damage after just a few hours of surface exposure, and the astronauts who brought that dust inside with them discovered something that changed the way engineers think about long-term lunar missions. The dust was not going to be a one-time contamination event. It was going to be a system, a cycle, and every time anyone went outside and came back in, the cycle would add another layer. Part 6. The infiltration problem. Here is where the engineering story gets genuinely unsettling. The challenge of lunar dust is not just that it is sharp and reactive, it is that it is extraordinarily good at going places. It is not supposed to go, and extraordinarily bad at being removed once it arrives. The Apollo spacesuit was a technological marvel for its time, and the dust defeated it anyway. Not catastrophically, not all at once, but steadily and persistently in ways that accumulated across every single EVA. That is an extravehicular activity, the formal term for going outside. Astronauts reported that after their first moonwalk, the suit's joint bearings moved differently. The fabric showed visible abrasion marks. The zippers and closure mechanisms that needed to function perfectly to maintain a pressure seal were gritty in a way that was difficult to fully clean. Photographs from the Apollo surface missions show spacesuits that went grey with dust within hours, and then the astronauts came back inside the lunar module and brought the dust with them because there was no way not to. The airlock procedure was designed to minimize contamination, but minimizing is not the same as eliminating. And in a confined space shared by two people and all of their equipment, even a small amount of resuspending dust creates a persistent airborne hazard. Harrison Schmitt, the geologist on Apollo 17, who spent the most time on the surface of any Apollo astronaut, described what he experienced inside the module as symptoms that resembled an allergic reaction: sneezing, eye irritation, throat inflammation, what he called lunar hay fever triggered by contact with the dust that had come in from outside. Now, Schmidt's exposure lasted hours, not weeks. His symptoms were real but temporary. The question that has haunted lunar planners ever since is what happens when the exposure is not hours but days, not days but weeks, not weeks but months, because the plans for a permanent lunar outpost involve all of those timescales. And the engineering paradox is brutal. There is no EVA that does not add to the contamination load. Every time a crew member goes outside to maintain equipment, to collect samples, to operate scientific instruments, they come back in with more dust. The habitat does not get cleaner over time. It gets progressively more contaminated. The abrasion on seals does not reset. It accumulates, and every accumulation increases the probability of a seal failure, a mechanical degradation, a system loss. The European Space Agency in its long-duration mission planning work has listed dust abrasion as one of the primary mission-limiting factors for any extended lunar surface stay. Not a background nuisance, a primary limiting factor, the kind of thing that determines whether a mission lasts the planned duration or has to end early. And that framing, dust as a mission ender, not just a maintenance headache, is worth sitting with because it is not the framing you hear in the press conferences. What it means is that the moon has a defense mechanism it did not design. It just has one, and it is made of the same material as the ground beneath your feet. Part 7. Apollo's first warning. The clues were there from the beginning. They just did not get the attention they deserved. Partly because the Apollo missions were so focused on the miracle of getting there and back at all, that the biological fine print got somewhat buried in the celebration of the larger achievement. Harrison Schmidt's reaction during Apollo 17 in 1972 was the most dramatic individual case, but it was not isolated. Virtually every Apollo astronaut who spent time on the surface reported some form of irritation upon returning to the lunar module. Eyes watering, throat scratchy, sneezing that did not have an obvious source until someone made the connection to the grey powder covering every surface. The dust was getting airborne inside the vehicle and the crew was breathing it. What made the Apollo experience a limited dataset for long-term planning was the duration. The longest any Apollo crew spent on the lunar surface was Apollo 17's 3 days. 3 days is enough to document immediate irritation. It is nowhere near enough to document chronic exposure effects. It is not enough to see what happens to lung tissue over weeks or months of continuous low-level inhalation. It is not enough to see how the immune system responds when it cannot fully clear the particles, because the exposure keeps refreshing. The Apollo missions gave us a warning sign. They did not give us enough information to know how serious that warning sign actually is. Post-mission medical evaluations noted the respiratory symptoms and filed them. Early NASA planning in the Artemis era initially focused on mobility, power systems, and life support architecture, the engineering challenges that were most tractable and most visible. Dust biology was for a time treated as a secondary concern, something to be addressed in later design iterations. That framing has been shifting. The scientific community working on lunar habitability has been increasingly vocal about the fact that the biological risk from dust is not a problem you solve with better engineering alone. It is a problem that requires knowing something about what long-term exposure actually does to a human body. And we do not have that data. The Moon provided the warning. The Moon is also the only place where the answer can be found. Part 8, the long-term unknown. Here is the knowledge gap that should keep mission planners up at night. We have never exposed a human being to lunar dust for longer than a few days. We have never studied what happens to respiratory tissue after weeks of continuous low-level exposure to particles with a specific chemical reactivity profile of space-weathered silicates. We have no longitudinal health data on any human who has breathed lunar dust in meaningful quantities, because every person who has ever been on the Moon left within days and returned to an environment with clean air and normal atmospheric pressure and standard medical care. What we do have is laboratory data, and the laboratory data is not reassuring. Studies using simulated lunar dust, ground-up terrestrial minerals designed to approximate the physical properties of regolith, have shown that exposure of lung cell cultures causes oxidative stress responses, which is the cellular equivalent of a fire alarm going off. It causes measurable DNA damage markers in the affected cells. It triggers inflammatory responses that in a real respiratory system over time could contribute to the kind of chronic inflammatory lung disease that is classified under the umbrella of silicosis. The critical word in all of that is simulated. The lunar dust simulants used in laboratory studies are almost certainly less reactive than the actual lunar regolith, because space weathering, the surface modification that happens when particles are exposed to solar radiation and cosmic rays for billions of years in vacuum, is not something you can fully replicate in a laboratory. The real particles are likely more chemically active than the ones being studied. The real biological effect is likely worse than the laboratory data suggests. This is not speculation. It is a consistent conclusion in the scientific literature on this topic. And it is the reason researchers in this field tend to write about dust toxicity with an emphasis on uncertainty rather than reassurance. And here is the additional layer that makes the uncertainty even harder to resolve. The dust problem does not exist in isolation on the Moon. A crew member breathing lunar dust while also receiving elevated radiation exposure is experiencing two simultaneous biological stresses, and the interaction between those stresses is not linearly additive. The immune system is suppressed by radiation exposure. A suppressed immune system is less capable of managing the inflammatory response triggered by dust inhalation. The lung tissue damage by reactive silica particles is more vulnerable to radiation-induced DNA damage than healthy tissue. The two hazards compound each other in ways that existing models cannot fully capture because there is simply no data on combined exposure effects in a lunar environment. No animal study, no human analogue, no simulation comes close to the real conditions. What Artemis missions are going to do for the first time is expose human beings to this environment for durations that will begin to generate real biological data. That is extraordinary from a scientific perspective. It is also, if you think about it carefully, a fairly significant statement about the gap between what we know and what we are about to do. We are returning to the Moon without a complete answer to the question of whether the Moon's most basic physical property, its surface material, can be tolerated by human biology over the timescales the mission requires. And if the dust alone is this complicated, wait until you hear about what is happening above the surface. Because up there, you cannot even see the thing that is trying to kill you. Part 9. No shield, no buffer. Let me put something in perspective that tends to get lost when people talk about space radiation. Right now, as you watch this, Earth's magnetic field is deflecting an enormous quantity of high-energy charged particles. The solar wind, a continuous stream of plasma ejected from the sun, is being guided around our planet by the magnetosphere, a region of magnetic influence that extends tens of thousands of kilometers into space, acting as an invisible shield. The Van Allen belts are trapping additional energetic particles in two donut-shaped zones around Earth. The atmosphere absorbs the radiation that gets through anyway, turning high-energy cosmic photons into lower-energy particle showers that mostly dissipate before reaching the ground. You're protected by a layered system of electromagnetic and atmospheric shielding, so effective that you never once have to think about it. The Moon has almost none of this. It has an extremely weak and irregular magnetic field, essentially the remnant patchwork of ancient magnetic activity that does nothing to deflect the solar wind at a global scale. It has no atmosphere. It has no Van Allen belts. What it has is direct, unmediated exposure to space. The full solar particle environment, the full flux of galactic cosmic rays coming from every direction across the galaxy, and the secondary radiation generated when primary particles hit the lunar surface and produce a spray of lower energy but still biologically significant particles from below. The ISS, for reference, still sits within Earth's magnetosphere. Astronauts on the station receive elevated radiation compared to the surface, but they have a partial buffer. On the Moon, that buffer is gone. You're standing in essentially open space on a rock with whatever shielding your habitat and your spacesuit can provide. And no matter how good that shielding is, it cannot solve the fundamental problem, which is that you're in the wrong place for a biological organism. This is not a risk that exists occasionally during bad solar weather. This is the constant baseline condition. It is the background hum of the lunar environment, the radiation that exists on the quietest day the sun can produce, the floor beneath all the other threats. And the survival challenge is not about managing it on the days it spikes. It is about managing it every single day for however long the mission lasts, while simultaneously managing everything else the Moon is doing to you. The radiation does not stop while you're dealing with the dust. The dust does not take a break while you're sheltering from a solar event. They're all happening at once all the time, and the human body was built for none of it. Part 10. The measured reality. We're not guessing about the lunar radiation environment. We have data, real instrument-measured data from the surface of the Moon collected by China's Chang'e 4 mission, which landed on the lunar far side in January 2019 and carried a radiation dimeter as part of its scientific payload. The number it measured was approximately 1,369 microsieverts per day. To understand why that number matters, you need a comparison. The average person on Earth receives roughly 3 microverts per day from all sources of background radiation combined. Cosmic rays, soil, building materials, medical imaging, all of it. The International Space Station crew typically receives somewhere between 200 and 400 microverts per day depending on solar activity and their specific orbit. On the Moon, you're receiving roughly double the ISS dose and roughly 200 times the Earth's surface dose every single day without a break. Over a 6-month mission, the cumulative exposure at that rate would substantially exceed the career radiation dose limits that NASA currently applies to its astronauts. Limits that were set based on estimated increased cancer risk from ionizing radiation. This is not a theoretical projection. This is arithmetic applied to a measured number. The radiation environment on the Moon at its normal quiet baseline is already in the zone, where extended missions require either significant shielding solutions, modified dose limit frameworks, or acceptance of elevated long-term health risk. The specific biological mechanisms are worth understanding because radiation as a word tends to flatten something that is actually a complex set of different physical processes with different biological consequences. Galactic cosmic rays are high-energy particles, protons, and heavier atomic nuclei, accelerated to near light speed by supernova explosions and other energetic events elsewhere in the galaxy. When they pass through biological tissue, they cause ionization, the stripping of electrons from atoms along a narrow track through the cell. That ionization can break chemical bonds, including the bonds in DNA. Most of the time, the cell's repair machinery fixes the damage, but the repair process is imperfect, and over thousands and thousands of exposures, the error rate accumulates. The long-term result is elevated cancer risk. For the central nervous system, there is growing evidence of cognitive effects, reduced neuroplasticity, impaired memory consolidation, changes in spatial reasoning that have been observed in animal studies of heavy ion radiation. Whether those effects translate to humans at the dose rates and durations of lunar missions is again something we do not yet know for certain. What we do know, and this keeps coming back to the central problem, is that the Moon's radiation environment is not safe. It is not intermittently threatening, and it cannot be fully solved by the engineering solutions currently available. Part 11. Solar Storms, the Sudden Killer. Everything discussed so far has been about the baseline, the constant, ordinary, unremarkable daily dose that the Moon receives when nothing unusual is happening. Now let us talk about what happens when something unusual happens. The Sun is not a stable object. It is a dynamic, churning plasma furnace undergoing continuous magnetic activity, and periodically that activity produces what are called solar particle events, sudden intense releases of high-energy protons and heavier particles associated with solar flares and coronal mass ejections. These events vary enormously in intensity. Most of them are manageable, some of them are not. The historical reference point that NASA engineers use when discussing worst-case scenarios is the event of August 1972. In the month between Apollo 16's return to Earth and Apollo 17's launch, the Sun produced one of the most intense solar particle events ever recorded in the instrumental era. Had either mission been timed differently, had there been astronauts on the lunar surface during that event, the outcome would likely have been lethal. The radiation dose delivered in the most intense phase of that storm was estimated at levels that would have caused acute radiation syndrome within hours and would have exceeded survivable exposure thresholds without adequate shielding. The problem with solar particle events is that they are not reliably predictable. Space weather forecasting has improved significantly since 1972, and there is now a monitoring network of satellites and instruments that can provide some warning when conditions on the Sun look threatening. But the lead time between detection and the arrival of a particle front at the Moon is measured in tens of minutes to a couple of hours, and that assumes the event was detected early, which is not always the case. For an astronaut on an EVA outside the habitat, the practical warning window before a major event could become immediately dangerous may be under an hour. 1 hour. That is the margin. And the question of whether an astronaut can reliably get from wherever they are on a lunar EVA back inside a shielded habitat within that window is a question that has no comfortable universal answer. It depends on how far they have travelled. It depends on whether their vehicle is functioning properly. It depends on whether the storm is developing faster or slower than the forecasting models predicted. It depends on luck in ways that mission planners are not supposed to rely on but cannot entirely engineer away. Every EVA on the Moon is a gamble against solar behaviour that no one can fully predict. The Sun has 17 billion years of remaining life and no particular interest in accommodating human schedules. The Moon has no atmosphere to slow anything down once the particles arrive, and the price of being outside at the wrong moment is not a sunburn. The probability of a major event during any single EVA is low, but across hundreds of EVAs over years of lunar operations, the cumulative odds begin to look very different. This is not a problem you solve. It is a risk you manage imperfectly for as long as people are on the surface. Part 12, the unsolvable part. Solar particle events, as terrifying as they are, have a partial solution. Go inside, get behind shielding. Wait it out. The storm passes. Galactic cosmic rays are a different category of problem entirely because they do not pass. They do not have an off switch, and the physics of shielding against them creates a problem that current engineering cannot resolve. Galactic cosmic rays include heavy atomic nuclei, iron nuclei, silicon nuclei, atoms stripped of their electrons and accelerated to fractions of the speed of light, and these particles are so energetic that they penetrate most shielding materials. Worse, when they interact with shielding material, they can produce secondary particles, a shower of lower energy, but still biologically significant radiation generated by the collision. This means that simply adding more shielding mass does not linearly reduce exposure, and can beyond a certain thickness actually increase it through secondary particle production. The engineering solution that has the best theoretical basis is burial. Building lunar habitats underground or under sufficient regolith cover to absorb the primary particles before they reach the occupied space. That solution is real and it is under active study. It is also not what the first Artemis surface missions will have. The first crews are going to be on the surface in structures that offer meaningful but incomplete radiation protection for missions that generate cumulative exposures that will exceed standard Earth-based occupational limits. That is not a failure of planning. It is the honest reality of what the physics allows with current technology. The radiation problem is not solved. It is managed to the extent that management is possible, and beyond that it is accepted as the price of being on the moon. And that price, the daily radiation dose, the solar storm risk, the permanent heavy ion exposure is being paid simultaneously with everything else the moon charges for its presence. Speaking of charges, let us talk about the temperature, because the thermal environment of the moon is its own kind of engineering nightmare, and it plays out over time scales that are unlike anything in terrestrial experience. Part 13, a 300 degrees climate swing. At lunar noon, standing in full sunlight on the equatorial surface of the moon, the temperature of the ground beneath your feet reaches positive 127 degrees C. That is above the boiling point of water. Exposed materials heat to the point where standard electronics fail, lubricants break down, and mechanical joints seize or deform. The thermal radiation pouring off the surface is intense enough to constitute a significant heating load on anything in contact with it. 12 hours of lunar time later, after the sun has set and the 2-a-long lunar night has begun, that same surface cools to minus 73 degrees. The temperature swing between those 2 points is exactly 300 degrees C, a range so extreme that it is difficult to find a material on Earth that encounters anything comparable in normal service conditions. Think about what 300 degrees of thermal cycling does to a bolt or a seal or a length of cable. Materials expand when heated and contract when cooled. The amount of expansion and contraction depends on the material's coefficient of thermal expansion, and over 300 degrees, even materials with relatively low expansion coefficients experience significant dimensional change. Every interface between two different materials in a piece of equipment, every joint, every seal, every connector, every fastener experiences that dimensional change differently because different materials have different expansion rates. Over one cycle, the effect is manageable. Over 10 cycles, 100 cycles, 1000 cycles, it is cumulative mechanical fatigue. Seals that were tight at the start of a mission develop gaps. Joints that moved smoothly begin to stick or play. Thermal stress cracks propagate through structural elements. The moon does not attack equipment the way a sandstorm attacks it. All at once, obviously visibly, the moon degrades equipment slowly, methodically, with every cycle of day and night in a way that is harder to detect and harder to predict. And this is the environment that any permanent human outpost must be designed to survive for years, not days. Apollo hardware was built to last for days. The engineering requirements for something that must last years for a habitat that must cycle through dozens of lunar days and nights while maintaining pressure integrity, thermal insulation, structural soundness, and mechanical function are qualitatively different from anything the Apollo program required, and the testing and validation of that hardware cannot be completed on Earth, because Earth does not have a 300-degree rethermal cycle. The first real test of long-duration hardware will happen on the moon in the conditions the hardware was designed to survive, and the results of that test will tell us things we cannot learn any other way. Part 14, the 2E night. The lunar night lasts approximately 354 hours. For the non-mathematicians in the audience, that is roughly 14. 7 Earth days, 2 weeks of continuous darkness, 2 weeks without a single photon of sunlight reaching the surface. And for a mission architecture that depends on solar power, which most proposed Artemis surface hardware does, at least in part, 2 weeks of darkness is not an inconvenience. It is a survival threshold. Solar panels are fairly obviously useless without sunlight. During the lunar night, any habitat, vehicle, or instrument that relies on solar power must either have an alternative energy source capable of sustaining it through 354 hours of darkness, or it must enter some form of hibernation mode and survive the cold and then successfully restart when the sun returns. The hibernation approach has been tested robotically. Various missions have attempted to survive lunar nights with varying degrees of success, and the consistent lesson is that surviving the temperature extreme of the lunar night is not guaranteed, even for well-designed hardware. Several robotic landers that were designed to attempt lunar night survival did not successfully restart in the morning. For human habitation, hibernation is not an option. A crew cannot hibernate. They need continuous power for life support, thermal control, communications, food preparation, medical systems, and the 100 other functions that keep people alive in a sealed structure on an airless world. The 2 night is therefore a fundamental design constraint. Every surface system must either produce its own power independently of solar input, or be connected to a system that does. Nuclear power is the most technically credible solution for long-duration lunar night survival, and NASA has been developing small fission surface power concepts under the OTMUS architecture. But those systems add mass, complexity and development time, and they introduce their own operational requirements and failure modes. The point is that the lunar night is not just a darkness problem, it is a compound problem. Cold plus power loss, plus the structural stress of thermal contraction, plus the requirement to restart complex systems after prolonged cold exposure. And it repeats every lunar month for as long as the mission continues. Every single night is another test. Part 15, Bullet Speed Space Dust. Here is something that rarely gets mentioned in the general public conversation about lunar surface hazards. Possibly because it sounds almost unbelievable until you run the numbers. The moon is continuously being hit by micrometeorites, particles ranging from grains of sand to small pebbles that arrive at an average velocity of approximately 20 km per s. 20 km per s. That is roughly 72,000 kmh. A rifle bullet travels at about 1 km per s. A micrometeorite arriving at 20 km per s carries the kinetic energy equivalent of an object going 20 times faster than a bullet. For a particle massing a single mg, 1,000th of a gram, about the weight of a small ant, the kinetic energy on impact is significant enough to pit metal surfaces, fracture glass, and penetrate materials that would stop a conventional projectile cold. On Earth, almost none of these particles reach the surface. They enter the atmosphere and ablate, burn up through friction with air molecules before they can hit anything. The atmosphere that protects us from the cold, from radiation, from the full force of the solar wind, also silently vaporizes the continuous stream of small impactors that the solar system throws at our planet every day. You're protected from a micrometeorite bombardment by every breath you take. The moon has no such protection. Every particle that crosses its orbit hits its surface at whatever velocity it happened to have. The flux is not enormous. The moon is not being peppered with visible impacts every second, but it is continuous. Over years, the cumulative effect on any surface infrastructure is real and measurable. Solar panels develop pits that reduce efficiency. Thermal coatings that rely on precise surface properties get degraded by impact damage. Transparent elements, windows, instrument covers, visors develop microfractures that scatter light and reduce visibility. The probability of a significant impact on any given habitat module during a short mission is low. The probability over years of operation is not. This is one more place where the moon's hostility is not the dramatic immediate kind. It is the slow, patient, cumulative kind. The kind that does not trigger an alarm the day it becomes a problem, but has been building since the day the equipment was deployed. The moon erodes things, just not in any way that looks like erosion from a distance. Part 16. Constant erosion reality. The surface of the moon is a geological archive of violence. Every crater, from the enormous impact basins visible to the naked eye from Earth to the microscopic pits visible only under an electron microscope, represents a moment when something from elsewhere in the solar system arrived without warning and rearranged whatever was there. There is no healing process. There is no infill, no overgrowth, no weathering that smooths the record. The moon remembers every impact it has ever received in perfect geological detail going back 4 billion years. What that means for anything humans place on the surface is that the bombardment that shaped the moon over 4 billion years is the same bombardment that is happening right now today at the same rate as always. The moon is not in a quiet period. It is not between events. The impacts are ongoing. The micrometeorites are arriving continuously, and the surface is being rearranged slowly, constantly without pause, the same way it always has been. That is the environment where we are proposing to build. Not a stable, inert platform, but an active impact zone that has been operating without interruption since the solar system was young. The timescales involved make it easy to dismiss the risk. The chance of a significant impact on a specific piece of equipment in any given year is genuinely small. But the moon does not operate on human timescales, and the longer any human infrastructure operates there, the more the moon's patience becomes relevant. But of all the things the moon is doing to challenge any long-term human presence, the one that came as perhaps the greatest surprise to modern scientists is happening below the surface. Because it turns out the moon, which we thought was a cold, dead, geologically inert world, is still moving, and what it does when it moves is something that no one fully anticipated. Part 17. The dead world myth breaks. When the Apollo astronauts placed seismometers on the lunar surface, instruments sensitive enough to detect ground motion at a fraction of a millimeter, Nobody expected them to be very busy. The moon was assumed to be geologically dead, a cold, rigid rock that had stopped doing anything interesting billions of years ago. No active volcanism, no plate tectonics, no significant internal dynamics, just a ball of ancient rock floating in space, geologically finished. The data that came back from those seismometers forced a significant revision of that assumption. Over the operational lifetime of the Apollo seismic network, roughly from 1972 to 1977, the instruments recorded over 13,000 seismic events. 13,000. The moon is not geologically dead, it is geologically active in a way that generates continuous seismic activity. And the character of that activity is in some ways more alarming than the equivalent on Earth. The most remarkable thing about lunar seismicity is what happens after the initial event. On Earth, when an earthquake occurs, the seismic waves travel through the planet, are absorbed by the relatively soft, partially molten water-saturated rock and die out within minutes. The ground shakes, and then it stops. On the moon, the rigid, cold, dry crust does not absorb seismic energy the way Earth's does. Instead, the waves bounce around inside it, reverberating and resonating in a way that has been described by scientists who studied the Apollo data as the moon ringing like a bell. A moonquake does not shake and stop. It shakes and then keeps shaking for minutes, sometimes for over an hour, as the seismic energy circulates through the rigid crust, finding no mechanism to dissipate. The implications for any structure built on the lunar surface are not trivial. A building designed to survive a 30-second earthquake, which is what most terrestrial earthquake engineering addresses, may behave very differently under an hour of continuous low-level vibration. The stress patterns are different, the failure modes are different, the fatigue loading is different, and the frequency and magnitude of seismic events on the moon is not fully characterized, which means the engineering margins that can be applied are based on incomplete data. Part 18, Moonquake Types. Not all lunar seismic events are created equal, and once you begin to separate them one by one, the moon stops looking like a quiet frozen world and starts to feel more like a system that is still in subtle ways alive. Not alive in the biological sense, of course, but active, responsive, under tension. What the early Apollo missions first detected was not a single type of shaking, but an entire spectrum of seismic behavior, and each type tells a slightly different story about what is happening beneath that grey, silent surface. The most common of these are what scientists call deep moon quakes. These originate far below the surface, somewhere between 700 and 1,200 kilometers down deep within the moon's interior. At those depths, the rock is under immense pressure, and the forces acting on it are not local but celestial. These quakes are driven by tidal stress. The gravitational pull of Earth, combined with the influence of the Sun slowly flexing the moon's interior as it moves through its orbit. If that sounds abstract, it helps to picture the moon not as a rigid sphere, but as something that is being gently squeezed and released over and over again in a predictable rhythm. That stress builds, releases, and then builds again. The result is a series of small seismic events that occur with remarkable regularity, tied almost like clockwork to the moon's orbital position. These deep moon quakes are not particularly strong. Most are low magnitude, barely noticeable compared to what we would consider significant on Earth, but they are persistent. They form what scientists often describe as the background hum of the moon, a constant low-level reminder that, even deep below the surface, the moon is not entirely still. Close to the surface, a different kind of process begins to dominate. Here the driver is not gravity, but temperature. Thermal moonquakes are caused by the extreme temperature swings that define the lunar environment. Over the course of a lunar day, which lasts about 2 weeks in Earth time, the surface heats up to over 100 degrees C. Then, as night falls, it cools dramatically, dropping to temperatures far below freezing. This cycle repeats again and again with no atmosphere to buffer the transition, no wind to distribute heat, no moisture to soften the change. The surface expands as it heats and contracts as it cools, and over time, that repeated expansion and contraction causes the outer layers of rock to fracture. These fractures don't happen all at once. They occur gradually, often clustering around the terminator, the moving boundary between day and night. As that line sweeps across the moon, it carries with it a wave of thermal stress. Rock that was just heated begins to cool. Rock that was frozen begins to warm, and in that transition zone the material is under strain. The result is a steady series of small seismic events. Individually, they are not powerful, but they are frequent. They represent a kind of surface-level instability that is always present, always shifting, always adjusting to the changing thermal environment. Then there are the impacts. On Earth, most incoming meteoroids burn up in the atmosphere long before they reach the ground, but the Moon has no such protection. Every particle that intersects its path, whether it's a tiny grain of dust or something larger, strikes the surface at full velocity. Each impact generates its own seismic signal, and because impacts are so common, especially at smaller scales, they contribute significantly to the total number of seismic events recorded. These impact-generated quakes are relatively easy to identify. They have distinct waveforms, signatures that stand out against the more regular patterns of deep or thermal quakes, and they serve as a constant reminder that the Moon is not just being shaped from within, but also from without. It is being struck continuously, but it is the final category, the one that received the most attention during the Apollo era and continues to raise the most concern today, that changes the picture entirely: shallow moon quakes. These occur much closer to the surface, typically within the upper few hundred km of the crust. And unlike deep moonquakes, their cause is not fully understood. They are thought to be related, at least in part, to the slow contraction of the Moon as it cools over geological time. As the interior loses heat, the entire body shrinks slightly, and that shrinkage creates stress in the crust. Faults form, blocks of rock shift, and occasionally that stress is released in a sudden measurable event. What makes shallow moon quakes so significant is not just their origin, but their intensity. Some of these events have reached magnitudes equivalent to around 5 on the RTR scale. On Earth, that level of shaking is enough to cause noticeable damage. Cracked walls, broken windows, objects thrown from shelves. It is not catastrophic in most modern cities, but it is far from trivial, and the Moon introduces a complication that Earth does not. On Earth, seismic waves are damped relatively quickly. The presence of water, fractured rock, and a more complex internal structure absorbs and disperses the energy. Earthquakes tend to be intense but brief. The Moon is different. It is dry, rigid, structurally simpler. When seismic waves travel through it, they are not absorbed as efficiently. Instead, they reflect, refract, and continue moving through the interior for much longer periods of time. The result is something that Apollo astronauts described in almost poetic terms. The Moon rings like a bell. A shallow moonquake does not simply shake the ground for a few seconds and then fade. It can produce sustained vibrations that last for minutes, with residual reverberations continuing for far longer. The energy lingers. It moves through the crust, bouncing and echoing in ways that make the experience fundamentally different from anything we're used to on Earth. And importantly, these events are not theoretical. The Apollo seismic network, limited though it was, recorded several shallow moonquakes during its operational period. This was not a global network with hundreds of stations. It was a small system operating for a relatively short time in a limited number of locations. And even with those constraints, it detected multiple events of this type, which raises a simple but important point. If we saw them, then we will see them again. For future missions, particularly those under the Aramis program, the challenge is not just understanding these events in isolation. It is understanding what happens when they interact with everything else the Moon is already doing. Because a lunar habitat is not placed on pristine, unchanging ground. It is placed on a surface that is constantly cycling through extreme temperatures. Materials expand during the day and contract at night. Over time, that creates microfractures, internal stresses, and gradual degradation. Now at a shallow moonquake, the structure is already under strain. The materials are already fatigued. And then suddenly the ground begins to move. Not violently perhaps, but persistently. Long enough for weaknesses to be tested. Long enough for connections to loosen. Long enough for small problems to become larger ones. And then after the shaking stops, the environment does not reset. The temperature continues to cycle. The dust continues to accumulate. The radiation continues to penetrate. And at some unknown point in the future, another seismic event will occur. Not on a predictable schedule, not with a clear warning, just another release of stress in a system that is still adjusting, still cooling, still changing. This is the part that shifts the perspective. On Earth, we often think of a foundation as something stable, something that can be trusted to remain in place while everything above it changes. It is the base assumption behind construction, behind architecture, behind the idea of permanence. On the Moon, that assumption becomes more complicated. The ground is not constantly in motion in a dramatic sense. You're not standing on something that is visibly shifting beneath your feet, but it is not static either. It is part of a larger system of forces, thermal, gravitational, and structural, that are always at work even if they are not immediately obvious. So the challenge for Artemis and for any long-term presence on the Moon is not just building something that can survive one event, it is building something that can endure a sequence of events. Events that may be small individually but cumulative over time. Events that interact with other stresses, temperature, dust, radiation in ways that are not fully understood. Events that test not just the strength of materials, but the assumptions behind how those materials are used. Because in the end, the question is not whether the Moon moves, it does. The question is whether we can build something that remains stable on a world that never fully is. Part 19. New Artemis Age Discovery. And this is where the story becomes a little more uncomfortable, because in 2024, a new study did not simply refine what we thought we knew about the Moon. It introduced a complication that sits directly beneath the exact terrain we're planning to use. Up until recently, the logic behind choosing the lunar South Pole as the primary target for human return felt almost straightforward. If humanity is going to live on the Moon for more than a few days, it needs access to something Earth makes feel ordinary: water. Not just for drinking, but for survival in a much broader sense. Water becomes oxygen. Water becomes fuel. Split it into hydrogen and oxygen, and suddenly you have the foundation for rocket propellant. That changes everything. It means missions no longer have to carry every resource with them from Earth. It means refueling could happen on the Moon itself. It means the Moon transforms from a destination into a gateway. And the only place on the Moon where that vision holds together, at least with current technology, is the South Pole. The reason lies in how sunlight reaches the lunar surface. Near the poles, there are craters so deep and angled in such a way that sunlight never touches their interiors. These permanently shadowed regions exist in a kind of eternal darkness. Temperatures inside them fall so low that volatile compounds, including water, can remain frozen for billions of years. Over immense stretches of time, water delivered by comet impacts and solar wind interactions becomes trapped in these shadowed pockets, preserved in a deep freeze that the rest of the Moon cannot sustain. When orbital missions began detecting strong evidence of water ice in these regions, it changed the conversation entirely. The Moon was no longer just a barren rock. It became a place where resources existed, resources that could support something more permanent than a brief visit. Without that ice, every drop of water needed for a mission would have to be launched from Earth at extraordinary cost. Life support would remain fragile, expansion would remain limited. But with ice, suddenly the idea of staying, of building, becomes possible. This is why the South Pole is not just an interesting location, it is for now the only location where a self-sustaining human presence on the Moon is even plausible. But the 2024 study introduced a complication that exists within that very promise. Using data from multiple recent orbital missions, researchers examined the geological structure of the South Pole region with far greater precision than had been possible before. What they found was not simply a frozen, inactive landscape. Instead, they identified structural features that had not been fully understood during earlier planning stages. They found fault structures, not ancient fractures that have been sitting untouched for millions of years, but features that show signs of relatively recent movement. On Earth, these kinds of structures would be associated with ongoing tectonic stress. Places where the crust is still adjusting, still shifting, still releasing built-up energy in small but meaningful ways. On the Moon, these features are often referred to as Labatt scarps. Small cliffs formed when one section of the crust is pushed up over another. They are the visible result of a slow global process. As the Moon cools over time, its interior contracts. That contraction may be subtle, but it is relentless. And as the interior shrinks, the crust must respond. It buckles, it fractures, it slips along fault lines, and some of those fault lines are located near and in some cases directly within the regions being considered for OTM landing sites. This is where the contradiction becomes unavoidable. The permanently shadowed craters, the ones that preserve the ice, are often embedded within complex terrain shaped by these same structural processes. The conditions that allow ice to survive, extreme cold, deep shadow, geological isolation, also overlap with areas that may not be as stable as we once assumed. In other words, the coldest, most stable-looking terrain on the Moon is not necessarily stable at all. The ice and the instability share the same ground. The resource we need and the risk we must manage are not separated by distance or geography. They exist together, layered into the same environment. From a mission planning perspective, this creates a tension that is difficult to resolve cleanly. The South Pole is essential because of the ice. Without it, long-term habitation becomes almost impossible with current technology. And yet the emerging data suggests that this same region may be more geologically active than previously understood. It is important to be careful here. The study does not claim that the South Pole is dangerous in an immediate or catastrophic sense. It does not suggest that large destructive moonquakes are constantly occurring in these areas. What it does show is that the assumption of complete geological stability, an assumption that quietly supported earlier planning decisions, may have been too simple. There is activity, there are faults. There is evidence that the crust in this region is still responding to internal stresses. What we do not yet fully understand is how often these faults move, how much energy they release when they do, and how that energy travels through the surrounding terrain. And that uncertainty matters because the type of infrastructure being planned for Artemis is not temporary. We're no longer talking about short visits measured in hours. We're talking about habitats, power systems, storage units, landing pads, and potentially even extraction systems designed to mine and process ice from within shadowed craters. These are structures that must endure not just a single mission, but repeated use over time. They must survive not just one hazard, but many, all interacting at once. Thermal cycling alone places materials under constant stress. During the lunar day, structures heat up and expand. During the lunar night, they cool and contract. This cycle repeats every 2 weeks over and over again. Over time, that expansion and contraction leads to fatigue. Tiny fractures form, connections weaken, materials degrade slowly but steadily. Now introduce a seismic event into that environment, even a moderate one. On Earth, a magnitude 5 earthquake is disruptive but manageable with proper engineering. It may crack walls or shift objects, but it rarely leads to total structural failure. On the Moon, however, the same magnitude behaves differently. The lack of moisture and the rigidity of the lunar interior mean that seismic energy is not absorbed as quickly. Instead, it lingers. It reverberates. It continues moving through the crust for extended periods of time. So a structure that has already been stressed by thermal cycling is now subjected to prolonged vibration. Not a brief shock, but a sustained shaking that tests its integrity over time. Seals may loosen, components may shift slightly out of alignment. Systems that rely on precision may begin to drift. And because the lunar environment offers no natural mechanisms for repair, no atmosphere, no moisture, no biological processes, any damage that occurs does not heal, it accumulates. This is the real challenge. It is not a single catastrophic event. It is the accumulation of smaller stresses, each one manageable on its own, but potentially significant when combined. And this is what the 2024 study forces us to confront. Not that the South Pole is inherently unsafe, but that it is more complex than we assumed. The very conditions that make it valuable are intertwined with conditions that may complicate long-term habitation. The ice is there, but so is the instability, and we do not yet fully understand how those two realities interact over time. There is also a broader implication here, one that goes beyond any single landing site. For decades, the Moon was treated as a stable foundation, a place where once you solved the problems of reaching it and surviving its environment, the ground itself could be trusted. It felt still. But the more we study it, the more that stillness begins to unravel. The Moon is not dramatically active, but it is not completely inert either. It is a body that is still cooling, still contracting, still adjusting, and that subtle activity matters when you're trying to build something that is meant to last. So the question shifts. It is no longer just whether we can reach the Moon or even whether we can survive there for a short period of time. It becomes whether we can build something that endures on a world that is not entirely stable. The answer for now remains uncertain. What the data tells us is that the original picture of a quiet, unchanging surface waiting to be occupied was incomplete. The reality is more layered, more dynamic, and in some ways more unpredictable. Which brings us back to the central tension. We are going to the South Pole because it is the only place that makes long-term survival possible. And we're going there at the exact moment we're beginning to understand that it may not be as stable as we once believed. The resource and the risk are not separate problems. They are the same problem, and we will have to solve them in the same place. Part 20. The strategic paradox. The water ice at the lunar South Pole is not optional. It is not a bonus feature or a convenient addition to an already viable plan. It is the foundation that the entire long-term strategy rests on. Without it, the vision of a sustained human presence on the moon begins to unravel almost immediately. At the most basic level, water is survival. It supports life support systems, provides oxygen, and sustains human crews. But on the moon, its importance goes far beyond that. Water is also fuel. When you split it into hydrogen and oxygen, you get the two primary components of rocket propellant. That single capability changes the entire architecture of space exploration. It allows missions to refuel off Earth. It reduces the mass that needs to be launched from the surface of our planet. And in spaceflight, mass is everything. Every kilogram you do not have to launch from Earth reduces cost, complexity, and risk. Without locally sourced propellant, every mission becomes an exercise in carrying everything with you. Fuel for the journey there, fuel for the return, fuel for contingencies. The numbers escalate quickly. Launch vehicles become larger. Costs multiply. Mission frequency drops. The idea of a continuous human presence becomes something fragile, dependent on a steady and expensive supply chain stretching across nearly 400,000 kilometers of space. With water ice available on the moon, that equation changes. You can imagine a different system, one where the moon supports itself at least partially. Crews can stay longer, missions can happen more often, infrastructure can expand rather than reset after each visit. The moon becomes not just a destination, but a node in a larger network of exploration. That is why the ice is not one resource among many. It is the resource that makes the entire concept viable. And yet the location of that ice introduces a different kind of problem. The permanently shadowed regions where these deposits exist are not just cold, they're permanently dark. They are places where sunlight has not touched the surface for potentially billions of years. The geometry of the moon's tilt and the depth of these craters combine to create environments that are isolated not just from heat, but from any direct solar input. This is what allows the ice to survive. Without sunlight, there is no energy to sublimate it into vapor and send it drifting off into space. The cold is constant, the darkness is absolute. The ice remains locked in place, preserved in conditions that are among the most extreme in the solar system. But those same conditions that preserve the ice also make these regions extraordinarily difficult to operate in. Imagine working in a place where there is no natural light ever. Not a dim twilight, not a reflected glow, but complete darkness. Every operation depends on artificial illumination. Every movement, every piece of equipment, every step taken by an astronaut must be guided by systems that themselves must function perfectly in an environment that is hostile to electronics, materials, and human perception. Now, add the temperature. In these permanently shadowed craters, temperatures can fall to around -250 degrees. That is colder than the surface of Pluto. At those temperatures, materials behave differently. Metals become brittle, lubricants freeze. Electronics must be specially designed to operate without failing. Even simple mechanical systems can seize or fracture under the stress. And then there is the terrain itself. These regions are not flat open plains. They are deep rugged craters with steep walls and uneven surfaces. Many areas have never been directly explored by surface missions. Our understanding of their structure comes primarily from orbital data, which, while advanced, cannot capture every detail that matters when you're placing equipment on the ground. So even without considering seismic activity, the challenge of operating in these regions is already significant. You're working in permanent darkness, at extreme cold, in terrain that is difficult to map and even more difficult to traverse without access to solar power as a primary energy source. Every system must be designed with redundancy. Power must come from alternative sources such as nuclear or stored energy systems, capable of surviving long periods without recharge. Communication systems must account for the unique geometry of the polar regions. Mobility systems must navigate terrain that has never been fully characterized at the human scale. Now, add the seismic question. The 2024 data suggests that the South Pole region is not as geologically quiet as previously assumed. Fault structures exist. The crust is under stress. There is evidence of ongoing, if subtle, activity. This does not mean that large catastrophic events are imminent, but it does mean that the ground itself cannot be treated as completely stable. And when you combine that with everything else, the picture becomes more complicated. The most critical resource for long-term survival is located in the most technically challenging terrain on the moon. That terrain is not just difficult because of temperature and darkness, but also because it may be subject to geological processes that introduce additional uncertainty. There is no easy alternative. Water ice does not exist in accessible concentrated deposits at lower latitudes. There are trace amounts bound within minerals and scattered across the surface, but not in forms that can be efficiently extracted with current technology. There is no substitute that can replace water's role in life support and fuel production. The mission cannot simply choose a more convenient location. It has to go to the South Pole, and the South Pole is more complex than it appeared. This is something the Moon seems to do consistently. The things you need most are never located in places that are easy to reach or easy to use. They're hidden in extremes, preserved in environments that test every assumption you bring with you. The ice is there, but it is locked in darkness. The terrain is accessible, but only with difficulty. The ground appears stable, but may not be entirely so. Every advantage comes paired with a complication, and that pattern is not just a matter of engineering. It extends into something deeper. Because if the Moon's geology presents a challenge for the machines we send there, the more fundamental question is what it does to the people inside those machines. Machines can be repaired, components can be replaced, systems can be redesigned when they fail. There is a margin for error, a capacity to iterate and improve. Human biology does not offer that same flexibility. The truth is that we know far less about how the human body responds to long-term lunar conditions than the confidence of current mission planning might suggest. We have data from short missions from Apollo where astronauts spent only days on the surface. We have extensive data from microgravity environments like those experienced on space stations. But the Moon exists in a space between those two conditions. Its gravity is not zero, but it is not sufficient to fully replicate Earth-like conditions either. At 1/16th of Earth's gravity, the body experiences a constant low-level unloading of weight. Bones are not stressed in the same way. Muscles are not used in the same way. The cardiovascular system adapts differently. We do not yet have long-term human data for this environment. We can make educated guesses. We can run simulations. We can study animal models. But we do not know with certainty how months or years in lunar gravity will affect the human body. Will bone density stabilize or continue to decline? Will muscles adapt or slowly weaken despite countermeasures? How will the immune system respond in an environment that combines partial gravity, radiation exposure, and potential contamination from lunar dust? These are not abstract questions. They are practical concerns that will determine whether long-term habitation is sustainable, and they exist alongside everything else. The extreme environment, the challenging terrain, the potential for seismic activity, the dependence on a single critical resource located in the most difficult place to access. All of it forms a single system of constraints, which brings us back to the underlying reality. The Moon is not designed to be inhabited. It does not offer resources in convenient places. It does not provide stable conditions by default. It does not adapt to us. Instead, it presents a series of challenges that must be solved simultaneously, each one interacting with the others in ways that are not always predictable. The ice makes long-term survival possible, but reaching it, extracting it, and using it safely requires navigating an environment that is far more complex than the original vision suggested. And beyond that, even if we solve the engineering challenges, we're still left with a question of whether the human body itself can adapt to a place like this. Because in the end, the machines are only part of the story. The real question is what happens to us when we stay. Part 21, the 16th gravity blind spot. There is a piece of fundamental biological data that simply does not exist anywhere in the scientific literature, and its absence is more important than it first appears. We do not know what 16th gravity does to the human body over months or years. Not approximately, not theoretically. We genuinely do not know. At first glance, that might sound like a narrow technical gap, something that can be filled in as we go. But this is not a minor unknown. It sits at the center of the entire question of whether humans can actually live on the Moon. Because everything we're planning, from habitats to mission durations to long-term outposts, quietly assumes that the human body will tolerate that environment well enough to function, and that assumption is built on incomplete evidence. To understand why, it helps to step back and look at what we do know. We have decades of data on what happens to the human body in microgravity, thanks to continuous research aboard space stations. In that environment, the body begins to change almost immediately. Bones, particularly those that normally bear weight like the spine, hips and legs, start to lose density. The rate is not subtle, it is measurable. consistent and significant, roughly 1 to 2% per month. That might not sound dramatic at first, but over time it compounds. In 6 months, an astronaut can lose a noticeable fraction of their bone mass. In a year, the loss becomes clinically significant. It begins to resemble the progression of osteoporosis, but compressed into a much shorter time frame. Muscles follow a similar pattern. Without gravity pulling against the body, many of the muscles we rely on for standing, walking and posture simply do not have to work as hard. The body adapts accordingly. Muscle fibers shrink, strength declines. Even with rigorous exercise routines designed to counteract this effect, some level of atrophy is almost unavoidable. Then there are the more subtle but equally important changes. Fluids within the body shift. On Earth, gravity pulls blood and other fluids downward. In microgravity, that distribution changes. Fluids move toward the head, creating a persistent pressure that the body is not accustomed to. Over time, this can affect vision, altering the shape of the eyeball and leading to a condition known as spaceflight, associated neurocular syndrome. It is not fully understood, and in some cases the effects do not completely reverse after returning to Earth. The cardiovascular system also adapts. The heart no longer has to work as hard to pump blood upward against gravity, so it begins to decondition. Blood volume decreases. Upon returning to Earth, astronauts often experience difficulty standing for extended periods, as their bodies struggle to readjust to the demands of a full gravitational environment. Even the immune system shows signs of change. Certain immune responses appear to be altered in microgravity, potentially making astronauts more susceptible to illness or affecting how their bodies respond to stress. And then there is balance and spatial orientation. Without gravity providing a constant reference, the inner ear, the system that helps us understand which way is up, becomes less reliable. Astronauts adapt over time, but the transition back to Earth can be disorienting. Taken together, these changes paint a clear picture. The human body is highly adaptable, but that adaptability comes at a cost. Remove gravity and the body begins to let go of the systems it no longer needs to maintain. The reassuring part is that many of these effects are reversible. When astronauts return to Earth, their bodies begin the process of rebuilding. Bone density increases, muscle mass returns, the cardiovascular system strengthens again. With time, rehabilitation and medical support, most astronauts recover a large portion of what they lost. But that recovery depends on something critical. It depends on returning to one gravity, and this is where the Moon introduces a complication that we do not yet fully understand. The Moon is not microgravity, it is not weightlessness. It has gravity about 1/16 of what we experience on Earth. That means there is a clear sense of up and down. Fluids still move in a recognizable way. You can stand, you can walk, even if that walk looks more like a series of bounding steps. At first glance, that might seem reassuring. 16th gravity is not nothing. It is a physical force acting on the body. It provides some level of mechanical loading on bones and muscles. It gives the cardiovascular system something to work against. But the question is not whether it does something. The question is whether it does enough. Bones and muscles are maintained through stress. They require a certain level of mechanical loading to preserve their structure. On Earth, gravity provides that load constantly. Every time you stand, every time you walk, every time you move, your body is reinforcing its own structure against that force. In microgravity, that load disappears and the body responds by reducing the systems that support it. In 16th gravity, the load is reduced but not eliminated. So what happens? Does the body interpret that reduced load as sufficient, maintaining bone density and muscle mass at a stable level? Or does it interpret it as insufficient, continuing to degrade those systems just at a slower rate? This is the question we cannot yet answer. Animal studies have provided some clues, but they are incomplete. Experiments conducted in simulated partial gravity environments suggest that some aspects of muscular skeletal structure are preserved better than in microgravity. Bones lose density more slowly. Muscles retain more of their mass, but the preservation is not complete. It does not match what is seen under full Earth gravity. And more importantly, animals are not humans. Their physiology is different. Their lifespans are shorter. The duration of these studies is limited. A few weeks or months of observation in an animal model does not translate cleanly into years of human experience. There is also the question of scale. A mouse in a controlled experiment is not performing the same range of activities as a human living and working on the Moon. The complexity of human physiology combined with the complexity of human behavior introduces variables that are difficult to replicate in a laboratory setting. And then there is the issue of time. The Apollo missions, for all their achievements, provide almost no data on long-term biological effects in lunar gravity. The longest any human has ever spent on the moon's surface is just under 3 days. That is not enough time for most of these physiological changes to become measurable. It is not enough time to observe trends. It is not enough time to answer the question. It is barely enough time to begin asking it. Which means that the first Artemis missions that involve extended stays on the lunar surface will be doing something unprecedented, not just in terms of exploration, but in terms of biology. They will be generating data that has never existed before. Every day spent on the moon will be in a sense an experiment. How does bone density change over weeks in 16th gravity? How does muscle respond to reduced loading even with exercise countermeasures? What happens to the cardiovascular system when it is partially but not fully challenged by gravity? And perhaps most importantly, how do all of these systems interact with the other stresses of the lunar environment? Because gravity is only one part of the equation, radiation exposure is higher, dust is more abrasive and potentially toxic, the environment is more extreme, the psychological conditions are more isolating. Each of these factors has its own effects on the human body, and they do not operate independently. They interact. Radiation may affect the immune system. Dust may affect respiratory health. Reduced gravity may affect how the body repairs itself. Together, they form a combined stress profile that no human has ever experienced for an extended period. This is what makes the gap in our knowledge so significant. It is not just that we do not know one variable. It is that we do not know how multiple variables combine. And yet, we are planning missions that assume a certain level of biological stability. We are designing habitats, scheduling rotations, and envisioning long-term stays based on models that are by necessity extrapolations. They are informed by the best data we have, but they are still predictions. And predictions in an environment like the moon carry risk, because if 1/6 gravity is not sufficient to maintain bone density over time, then long-term residents may face progressive skeletal weakening. If muscle loss continues even at reduced rate, then physical capability may decline over the course of a mission. If cardiovascular changes persist, then returning to Earth or even functioning effectively on the moon may become more challenging. These are not hypothetical concerns. They are direct consequences of what we already know about how the body responds to reduced gravity. The only question is where the threshold lies, and we do not yet know where that threshold is. Which brings us back to the central issue. The gap between what we know and what we are planning to do is not a minor detail. It is not something that can be quietly resolved in the background. It is central to the survival challenge that the moon represents. We're not just sending humans into a harsh environment, we're sending them into an environment where one of the most fundamental variables, gravity itself, exists at a level we have never experienced for long durations. We are in effect asking the human body a question it has never had to answer before. Can you adapt not to the absence of gravity and not to its full presence, but to something in between? And the only way we will find out is by going part 22, the biological drift problem. Let us follow the physiology a little further because the individual effects on their own are already concerning. But it is the way they interact with each other that begins to create something far more serious for long-duration lunar missions. In isolation, each system change can be managed, bone loss can be slowed, muscle decline can be partially countered, immune changes can be monitored. But when all of these shifts occur at the same time in the same body under the same environmental stress, the result is not a simple list of medical issues. It becomes a system-wide drift away from normal human biology. Bone density loss in 1/6 gravity is expected to be slower than in 0 gravity. But the critical detail is that slower does not mean stopped. Mechanical loading is still reduced compared to Earth. That means over weeks and months the skeletal system is still receiving less stress than it evolved to expect. And bone is not a static structure. It is constantly being rebuilt based on the forces placed upon it. When those forces decrease, the body begins to remove material it considers unnecessary. At first, the change is microscopic. Then it becomes measurable. Over longer periods, it becomes clinically significant. That progression matters because bone is not just structural support. It is the foundation for everything attached to it. Muscles depend on it for leverage. Joints depend on it for alignment. Even internal organs are indirectly influenced by the posture and structural stability it provides. As bone density decreases, the entire mechanical system of the body begins to shift. Fracture risk increases not only from impact but from reduced structural resilience. The skeleton becomes less like reinforced architecture and more like a structure that has slowly been thinned from within. On Earth, this process is already understood in the context of osteoporosis. In space, it is accelerated. In microgravity, astronauts respond with carefully designed countermeasures, resistive exercise devices, carefully structured physical training routines, and in some cases, pharmaceutical interventions aimed at slowing bone resorption. There is also a psychological safety net in place. The knowledge that after the mission ends, return to Earth gravity allows for partial recovery. The body is stressed, but it is not permanently removed from its baseline environment. On the Moon, that safety net changes. Exercise is still possible, but the loading conditions are different. Equipment must be adapted to partial gravity, which alters how resistance translates through the body. Pharmaceutical options are limited to what can be delivered and stored in a constrained environment with no possibility of rapid resupply. And perhaps most importantly, return to full Earth gravity is not part of the normal cycle of recovery. Astronauts cannot simply come back every few months to reset their physiology. They remain in the same reduced gravity environment that is producing the change in the first place. So the body continues to adapt, but without ever fully reversing those adaptations. That is a subtle but important difference. Now add the immune system into this picture and the complexity increases significantly. There is consistent evidence from spaceflight research that the immune system behaves differently outside Earth's surface environment. Certain immune cell populations show altered activity levels. Viral latency appears to shift with dormant viruses in the body sometimes becoming reactivated. Inflammatory markers change in ways that suggest the immune system is operating under a form of chronic stress. It is not a simple weakening or strengthening. It is a reconfiguration of how immune responses are regulated. The exact mechanisms are not fully understood, but multiple contributing factors have been identified. Radiation exposure is one. In low Earth orbit, astronauts are partially protected by Earth's magnetic field. On the Moon, that protection is significantly reduced. Galactic cosmic rays and solar particle events reach the surface environment with far greater intensity. That means cells are exposed to higher levels of ionizing radiation over time, which can directly affect immune function. Then there is psychological and physiological stress. Isolation, confinement, disrupted circadian rhythms, and operational pressure all contribute to hormonal changes in the body. Stress hormones like cortisol influence immune activity, often suppressing certain responses while altering inflammatory regulation. Sleep disruption adds another layer. On the Moon, daylight cycles are not Earth-like. A lunar day is roughly 29 Earth days long. That means humans living there must rely entirely on artificial lighting and scheduling to maintain circadian rhythm. Even small disruptions to sleep patterns have measurable effects on immune function over time. And finally, there is the microbiome. The community of bacteria in and on the human body plays a crucial role in immune regulation. In space environments, that microbiome appears to shift, likely due to changes in diet, environment, radiation, and hygiene constraints. These shifts may influence immune stability in ways we're only beginning to understand. Now, place all of these factors together in the lunar environment. Radiation levels are higher than on the International Space Station. Environmental stresses are more extreme. Sleep regulation is more difficult. Dust exposure introduces a new inflammatory challenge entirely. Lunar regolith is not like Earth's soil. It is sharp, abrasive, and chemically reactive. It can irritate skin, eyes, and potentially respiratory systems if inhaled. That creates a constant low-level inflammatory burden on the body. The result is not a simple weakening of immunity. It is a system operating under sustained pressure from multiple directions at once. It is adapting but continuously and in ways that may not be fully protective in all situations. So the critical question becomes what happens when a system in that state encounters a real medical challenge, an infection, a physical injury, a dental emergency, even something routine like a small cut becoming inflamed, or a minor respiratory illness. On Earth, these are manageable situations. There are hospitals within reach, there are specialists available, there are supplies, diagnostic tools, and the ability to escalate care quickly if needed. Even in remote environments, evacuation is often possible within hours. On the lunar surface, that safety infrastructure does not exist. Medical care is limited entirely by what has been prepositioned and launched from Earth. There is no blood bank that can be resupplied quickly. There is no hospital 20 minutes away. There is no specialist who can be called in for a complex procedure. Every medical intervention must be anticipated in advance, packaged and sent along with the mission. That creates a very different kind of medical environment. It is not just resource limited, it is time static. If something happens that was not planned for, the options are constrained by what is already present. And that is where the biological changes become more significant. Because the body is not operating in isolation. It is changing over time in multiple systems simultaneously in response to an environment that is itself continuously applying stress. Bone density is shifting, muscle mass is adjusting, immune function is adapting, cardiovascular conditioning is changing, sleep cycles are being managed artificially, psychological stress is present throughout. None of these systems are failing outright, but none of them are remaining perfectly stable either. This is the biological drift problem. It is not one thing going wrong. It is the gradual accumulation of small physiological changes across multiple systems all occurring at the same time in an environment where recovery is limited and external support is minimal. Every week spent on the Moon is another week slightly farther from the biological baseline that Earth provides. The body is constantly adjusting, but it is adjusting to a condition that is itself already altered. And the most important point is this. No human being has ever been observed in this exact combination of conditions for a meaningful duration. We have never studied sixth gravity over months or years in humans. We've never combined that gravity level with sustained radiation exposure, lunar dust environments, isolated medical systems, and extended mission durations. We're assembling all of these variables into a single environment for the first time, and the biology will not respond to each variable separately. It will respond to the combination, which means that even with careful planning, even with advanced countermeasures, even with extensive preparation, there remains a fundamental uncertainty at the center of everything. We do not yet know what long-term human life in lunar gravity truly looks like. We know pieces, we know fragments, we know how the body behaves in microgravity, we know how it behaves on Earth. We have partial models for reduced gravity, but we do not yet have the lived biological data that comes from months or years of continuous exposure to the Moon itself. And until we do, every long-duration mission is not just exploration, it is observation, it is data collection at the edge of human experience. And it's happening in an environment where the margin for biological error is extremely small, and the system under observation is the only one we have, Part 23 psychological isolation. There is a layer of this challenge that does not show up in blood tests, imaging scans, or even the most advanced physiological models, but it has consistently emerged as one of the most significant limiting factors in every long-duration human isolation study ever conducted. It is the psychological environment of the Moon, and in some respects, it may be the most alien aspect of the entire experience. This is because the human brain does not interpret environments in purely scientific terms. It responds to patterns, signals, and sensory cues that have been reinforced over millions of years of evolution. On Earth, those cues are everywhere. They're constant, layered, and deeply familiar. The Moon removes almost all of them at once. Step outside a lunar habitat, and the first thing that confronts you is the sky. It is not simply dark in the way people imagine night on Earth. It is not the deep blue-black seen from a high-altitude aircraft, nor the gradual fading of colour experienced during twilight. It is black in a more absolute sense. A complete absence of atmospheric scattering means there is no diffusion of sunlight. The sky is not filled with colour gradients or atmospheric depth. It is space itself, uninterrupted and immediate. Even in daylight, the sun does not illuminate the sky. It sits as a harsh, unfiltered white disk against a perfectly black background. There is no softness to it, no atmospheric halo, no shifting brightness that signals weather or time in the familiar earthbound sense. Shadows are sharp and absolute. Light behaves in a way that feels almost artificial, as though it has been turned up to maximum contrast and left there permanently. In that same environment, stars are visible even during what would be considered daytime. This is not poetic exaggeration. It is a direct consequence of the absence of atmosphere. There is no scattering medium to wash out the faint light of distant stars, so they remain visible, constant, and unchanging regardless of the sun's position. And there is no weather, no clouds moving across the sky, no wind carrying dust or moisture in visible patterns, no storms building on the horizon, no rain, no snow, no atmospheric perspective that allows distant features to fade gently into haze. On Earth, even the most barren desert is still dynamic. Light shifts, air moves, temperature changes create subtle cues that the environment is alive in a meteorological sense. On the Moon, none of that exists. The visual environment is fixed, unchanging, stark in a way that has no real terrestrial equivalent. The ground beneath your feet is similarly devoid of the familiar cues that make environments feel alive. There is no erosion happening in real time, no plants bending in wind, no water carving small changes into the landscape. Everything appears static, as if time itself has been slowed or removed from the surface entirely. And then there is a sound, or more precisely the absence of it. Outside the habitat in vacuum there is no medium for sound to travel through. That means there is complete silence in the physical environment, not the quiet of a remote forest, or a deserted mountain range where subtle natural sounds still exist. Not even the muffled silence of a snow-covered landscape. It is absolute. No wind, no distant movement, no ambient noise of any kind. Inside the habitat, sound returns, but only as something engineered. Fans circulate air, pumps regulate systems, electronics hum a dill in the background. Every sound is functional, intentional, mechanical. There is no wind pressing against a structure, no rain tapping against a surface, no birds calling in the distance, no insects, no flowing water. The audio environment is not discovered, it is constructed. This matters more than it might seem at first because the human nervous system is deeply tuned to natural soundscapes. For most of human history, sound has been one of the primary indicators of environmental stability. Wind suggests weather systems, water suggests life. Animal calls suggest ecological balance. Even subtle ambient noise provides reassurance that the environment is functioning as expected. When those cues are removed and replaced entirely by mechanical consistency, the brain does not interpret the silence neutrally, it interprets it as absence. Then there is Earth itself on the near side of the Moon. Earth is present in the sky as a large suspended sphere. It is bright, familiar, and visually dominant. It does not behave like other celestial objects. It does not rise and set in the same way the sun or stars do. It remains fixed in position, slowly rotating, always visible. For many astronauts, it functions as a psychological anchor, a constant reminder of origin, a visual connection to everything that is known, inhabited, and socially continuous. But on the far side of the Moon, that anchor disappears entirely. There is no direct view of Earth, no blue-white disk in the sky, no visible reminder that the planet exists. The crew is not just physically distant, they are visually disconnected from home. Communication requires relay satellites, meaning even the sense of direct line of sight connection is gone. Messages travel through infrastructure rather than open space visibility, and layered on top of that is time delay. Even when communication is possible, it is not instantaneous in the intuitive sense that humans are used to. There is a lag, a disruption in conversational rhythm that prevents the natural flow of interaction. That may seem minor on paper, but in practice it changes how social connection feels. Conversations become structured rather than spontaneous. Emotional exchange becomes slightly asynchronous. The sense of shared presence is weakened. To understand why this matters, it helps to look at Earth-based analogies. One of the closest comparisons we have is Antarctic winter over syndrome observed in crews stationed in isolated polar research bases during the long Antarctic winter. These environments share some key features with lunar missions: isolation, confinement, extreme conditions, and limited external contact. In those studies, researchers have consistently observed a cluster of psychological effects. Cognitive performance can decline over time. Attention becomes more difficult to maintain. Emotional responses can become blunted or exaggerated. Sleep cycles often become disrupted, especially in environments where natural light cues are absent for extended periods. Interpersonal dynamics also shift. In small isolated groups, minor conflicts can escalate more easily. Communication can become strained. Social withdrawal can occur. In more severe cases, individuals may experience more significant psychological distress. But even in Antarctic conditions, there are important differences that provide stabilizing factors. Crew members can still see a horizon. They can still step outside and breathe air that is part of a planetary atmosphere. They can still experience weather, even if only occasionally. They can still see the sun filtered through an atmosphere, and they can still feel connected to Earth through real-time communication without delay. None of those stabilizing factors exist on the Moon in the same way. The lunar environment removes not just physical familiarity, but also many of the subtle sensory inputs that the brain relies on to maintain a sense of normality. The result is an environment that is not just isolated, but perceptually disconnected from almost all Earth-like reference points. And crucially, the psychological effects of this environment have never been tested over long durations. Apollo missions provided extraordinary data, but they lasted days, not months. The crews were highly trained, tightly coordinated, and continuously supported. They experienced isolation, but only in short bursts relative to what future missions will involve. The Artemis missions will extend this timeline significantly. Crews may spend weeks or months on the lunar surface, and in doing so, they will become the first humans to experience the psychological effects of sustained lunar living in real operational conditions. That means they are not just participants in exploration. They are in a very real sense subjects in an unprecedented form of environmental psychology study. And what makes this particularly important is that psychological condition is not separate from mission performance. It is not an isolated domain that can be treated independently from engineering, biology, or operations. It directly affects how well crews can respond to everything else. A cognitively impaired crew may process information more slowly. An emotionally strained crew may communicate less effectively. A group experiencing interpersonal tension may have reduced coordination during high-stakes operations. Even small reductions in cognitive clarity can have disproportionate effects when the environment leaves no room for error. In other words, the psychological environment becomes part of the risk structure itself. It is not just background. It is not just context. It is a functional layer beneath every other system influencing decision and reaction time, cooperation and resilience. And unlike many of the physical risks, it cannot be measured directly in advance with high confidence. It must be experienced to be understood, which leads to a final, unavoidable conclusion. The Moon is not only a test of engineering or physiology, it is a test of perception, cognition, and psychological endurance under conditions that remove almost every familiar reference point humans rely on to interpret reality. We can model the physics, we can estimate the biology, we can simulate parts of the environment, but the psychological experience of living in that environment for months at a time is still largely unknown. And that unknown does not sit at the edge of the mission, it sits at the center of it. Part 24, the final question. Let me bring all of this back to the single question that matters, not can humans visit the Moon? Apollo answered that definitively and magnificently half a century ago. The question that Artemis is actually asking, whether it frames it that way publicly or not, is something much harder. Can humans persist on the Moon? Can they live there in a meaningful sense of the word? Not for hours or days under the adrenaline of a first landing, but for weeks and months in the grinding reality of a survival environment that never gives them a break. Can they maintain their biology, their bones, their lungs, their immune systems, their minds against the continuous compounding pressure of dust and radiation and thermal extremes and seismic uncertainty and isolation? Can the machines they depend on survive the thermal cycling, the micrometeorite bombardment, the dust infiltration, the regolith abrasion, the seismic loading for long enough to be useful? Can the engineering margins be maintained over time? Or does the Moon wear everything down faster than it can be repaired? These are not rhetorical questions. They are the actual open questions in the Artemis program. The ones that are not answered by the engineering analyses that have been completed, or the analog studies that have been conducted, or the robotic missions that have preceded the human ones. The only way to answer them is to send people and find out. And that is, in a sense, the honest framing of what Artemis is. It is not primarily an exploration program in the way Apollo was an exploration program. It is an endurance test, a long-term experiment in human survival in an environment that was not designed for us and does not accommodate us in any meaningful way. The Moon does not resist violently. It does not send storms or predators or seismic catastrophes on any particular day with any particular intention. It resists consistently. It resists with its chemistry, its physics, its thermal cycles, its radiation field, its geology, its silence, and its unbroken, unchanging sameness. It resists in the way that any environment resists a species that did not evolve there patiently, pervasively, on every timescale simultaneously without malice and without mercy. Apollo taught us that humans can survive a brief visit to the moon if the engineering is good enough, and the mission is short enough, and the luck is reasonable enough. What it could not teach us, because no one stayed long enough to find out, is whether humans can actually tolerate that environment over time. Whether the biological and psychological systems that define what we are can maintain themselves in a place where every single background condition is antithetical to their operation. Artemis is going to begin to answer that question. The data it generates will be the most important data in the history of human spaceflight because it will be the first real test of whether we are capable of the thing we've always assumed we were capable of. The moon has been waiting for 50 years. Its patience is not evidence of welcome, it is evidence of indifference. And the difference between those two things is something we're about to find out. Final takeaway. We went to the moon 6 times. We walked on it 12 times. We drove vehicles across it, planted instruments in it, collected over 840 pounds of it, and brought it back to Earth. We looked at Earth from its surface and described the view with words that are still quoted 50 years later. By every reasonable measure, Apollo was one of the greatest achievements in the history of our species. And then we stopped. We stopped for reasons that were primarily political and budgetary, and we told ourselves that the science was done, the achievement was real, the capability was proven. We told ourselves we understood the moon. We told ourselves we had been there and we knew what it was. The subsequent 50 years of science have quietly, persistently, methodically undermined most of what we thought we knew. The dust is not inert powder. It is a biological hazard whose long-term effects on human lungs remain uncharacterized. The radiation environment is not occasionally dangerous. It is continuously, measurably 200 times more intense than anything humans have evolved to tolerate. The temperature cycle is not an engineering footnote. It is a material degradation system that repeats with lunar precision, wearing down everything we build. The ground is not stable. It moves. It rings. And the specific terrain where we need to be because the ice is there show signs of active faulting that were not fully understood until 2024. The body in lunar gravity is not a known quantity. It is an untested biological system in an environment it has never experienced for the durations we're now planning. None of this means Artemis should not happen. The case for returning to the moon is real. The science, the technology, the resources, the strategic rationale for human expansion into the solar system. The reasons to go are genuine and significant, but the moon is not going to make it easy. It is not going to reward confidence with success. It is not going to forgive the gap between what we assumed and what the science actually says. It is going to do exactly what it has always done, present a compounding, simultaneous, unrelenting suite of hazards to every system, mechanical, biological, psychological, that human beings bring into its environment. And the question of whether those systems can hold over time under those conditions is one that no mission has ever stayed long enough to answer. We have always talked about the moon as a destination. The next chapter will reveal whether it is actually a home. And the terrifying, clarifying, genuinely important truth is this. We do not know yet after everything we have built, everything we have studied, every instrument we have landed, and every photograph we have taken, and every kilogram of rock we have brought home and analysed. After all of it, the most honest statement we can make about long-term human life on the moon is that we are not sure it is possible. We're not going back to explore the moon.